Hello, my name is Karla Martinez. Today I will be walking you through Lab 11. For this lab, we will encounter the concepts of a pendulum, gravity, gravitational acceleration, and Newton's first law of motion. So a pendulum is a simple mechanical system that consists of a weight suspended from a fixed point so that it can swing freely back and forth due to gravity. The motion of a pendulum is an example of periodic motion and can be classified as harmonic motion. And here are some examples of pendulums. We have wrecking balls or people on a swing, as you can see on the pictures. So my research question for this experiment is, how do mass, length of the string, and release angle affect the motion and acceleration of a simple pendulum? How can we use these to calculate the period of a pendulum? And my hypothesis is that length and angle will have more of an effect on the pendulum, while mass will have a more negligible impact on the period. Here are some of the theorems and formulas you should keep in mind when performing this experiment. Like we saw during the lab on pivot, by recording a pendulum's length, release angle or displacement, mass, total time, and oscillations, we are able to determine its period, which allows us to analyze the gravitational force of that pendulum. This is useful in many engineering fields as it provides engineers with a good understanding of the conditions around whatever it is they're building. And here are the theorems that you should keep in mind. For the case of this lab, we will use this calculation right here for tangent to calculate the angle of displacement for each trial in degrees. And we will use the time divided by the oscillations to calculate the period of each trial in seconds. Here are the differential equations to express harmonic motion of the pendulum. So harmonic oscillation refers to a type of periodic motion where a system oscillates back and forth around an equilibrium position. The key characteristic of harmonic oscillation is that the restoring force acting on the system is directly proportional to the displacement from the equilibrium position and acts in the opposite direction. This relationship results in a motion that is sinusoidal in nature, and you can find this in the book actually. And the differential equation that describes it is the first one that you can see here. So in this equation, x is the displacement of the system as a function of time. Omega is the angular frequency, which is related to the physical parameters of the system. And for the general solution, the a and b constants are determined by the initial conditions of the system, such as the initial displacement and the velocity. And then we can also use trigonometric identities, so it can be expressed in a slightly different form where you can see the amplitude of the oscillation and the phase angle, which represents the initial phase of the oscillation. This form of the solution is more convenient when we want to know the amplitude and the phase. So here are some of the things that we're measuring today. We're measuring the length of the string, the mass of the weight that we're hanging from the pendulum, the displacement, time, and the number of oscillations. And here are some of the tools for this lab. As you can see, we require a hook that is longer than 120 centimeters, and this is all described in the lab manual. We also require objects of different masses. I chose 3 objects and called them A, B, and C. We also require measuring tools such as a scale and a ruler to measure the mass of the objects and the displacement from the point of rest of each object. And as you can see, I chose different weighted objects and I made sure to write their exact measurements here. So steps. I have my pendulum, now what? So the first step is positioning the mass. First, you want to put your mass on the pendulum at your desired length and have it be at rest so you can choose what point of the mass to take as reference for displacement. In my case, the first picture on the left, you can see that the mass is at rest, and I drew a line on the bottom of the base so I can see where my middle point is at all times. For step 2, you want to grab your object and drag it towards you with the displacement you chose for that trial. I chose 3 centimeters for my first trial, so I moved the object 3 centimeters in the x-axis. Step 3, you want to release the pendulum without applying any force to it and let it complete a full swing. You will be able to see this more easily in the video. And step 4, you want to start your timer when the pendulum is at the position you released it from and count 1 oscillation when it goes all the way forward and back to you. And count as many oscillations as you want and stop the timer when the object has made its way to the starting position you released it from for the last oscillation. Hello, my name is Karla Martinez. I am taking Physics 1 with Professor Ene. So I'm going to be doing Lab 11 for a simple pendulum, and I'm going to be measuring the length of the string and the different angles and different masses. So after seeing the demonstration of the project, you can kind of see the data and results that I got. So the one that I demonstrated was object A, and as you can see, these are my results from changing the angle. And then I included the same trial with 3 centimeters, but changing the mass. And then I kept everything constant except for the length of the string for the third part of the experiment. And I used object B since it was the one with the least amount of weight. And that is also something that is pointed at in the lab manual that you can find. And as you can see, the relationship that I got was that pretty much the thing that has the most impact on the period is actually the length of the string. And there's a little bit of change as well with the angle. But that also depends on how well you follow the harmonic motion formula for small angles, since it mostly applies to small angles. So if you were to measure a much bigger angle, then that would change. And the change in mass is not all there, and we can attribute that difference in error in measuring, and just be sure to measure those uncertainties when you're performing your experiment as well. So my conclusion was pretty much that the length of the string was the biggest influence on the period of this pendulum. So some important applications or real life examples of um, pendulums in real life are that, of course, you usually have like your attractions in um, theme parks and things like that, or um, grandfather clocks or swings, like I mentioned earlier. But one of the biggest ones is seismometers, actually. So pendulums are a crucial component in seismometers. So they can be used as instruments that detect and measure um, se- seismic waves generated by earthquakes. The pendulum's motion is recorded when the ground shakes, allowing scientists to analyze the strength and location of the earthquake. And the reason I mentioned this is because currently there's been actually a lot of earthquakes around the world, especially right now. There's rumored to be one in Japan that they're bracing for. And I think that it's really good that we're learning about the tools that can be used to measure these things and to prevent and prepare for disasters like that. So, pendulums are one of those things. And that's a really cool fact. Thank you. So, if you have any more questions, you can refer to the textbook chapters. I believe chapter 14 and 15, especially, for additional information on pendula. And here are my references. I mostly use the book and anything from the lectures and anything that Professor Ene shared with me during office hours. Thank you.